At the beginning of our practice, we were given a bar of steel of 1018 steel, and we had to get from that bar 4 different pieces of material for about 1 centimeter thickness. So we cut the bar and we remove the leftover material. Then we mark our pieces with our team number and our type of steel with a marker machine. One of those pieces was instantly prepared for metallography test with the backlit, and as we did in last practices. The other three were left aside. So, as one part of the team was doing that, the other part of the team was preparing a mixture for the cementation process. This mixture was 83 to 87 crushed vegetal coal, 2 to 3% sodium carbonate, 10 to 12% barium carbonate, and 3 to 4% calcium carbonate. Once we had our mixture ready, in a box, we put a small layer of the mixture, and then we put our 3 pieces in separate spaces between them, about 5 millimeters. Then we sealed that box with clay and with cover, and we started the process. At first, we heat the oven to 900 degrees Celsius for 12 hours. So the next day, we took out the box, and one of the pieces was instantly quenched in water. The 2 remaining pieces were put back into the oven at 800 degrees for 15 minutes. Then we took out the pieces and quenched both of them in water. Then one of them was put again in the oven, this time for 15 minutes at 200 Celsius degrees. Once we had that, we also prepared the 3 pieces for metallography test. So once we had the 4 pieces, we apply a Vickers test to all of them 15 times, moving 50.
The objective of this practice is to apply the principles of solid-state diffusion to cement carbon steel rods in order to increase the mechanical properties of the outer layer and provide adequate tension.
La ventanita con la que vamos a cerrar la caja. Tamizares más de materiales.
Si no, se escucha más ingeniería. Tú, ¿qué es? Como me dicen. Los muchachos de ahora no tienen respeto ni por su nombre.
Estás jugando con plastilina.
Te quede bien sellada toda la
Huele bien feo eso.
¿En serio?
This practice I learned what the carburization process is and that it has tons of applications in the modern day industry. And as the Vickers results showed us, that indeed the carburization increases the hardness of a metal.
In our grain size test, we found that the number of grains was 12 at 900, 20 at 800, and 42 at 200. Like this was the last process of it. So using this formula of the grains, we found that the grains per over inch square is at 900 is 300, at 800 the second one is 500, and 200 the last one process is 1050. Now, in order to calculate the ASTM number, which is the n, the minus n, it's 9.2, 9.96, and 11. This means that in the exterior part we found smaller grains, but a lot of them. And it goes to the center, we found bigger grains, but less of them. For our Vickers test, in order to see the hardness of the different heat treatments, we first found that at 900 degrees, and only that process, the hardness was increased, finding that our material is 1018 steel, with meaning that it has 18% of carbon, and we see an obvious increase on the hardness, because the hardness of the material is 231, and we can see that in the outside of our material we got almost 850 and something really close by it, so meaning that the outside part is harder than the core, meaning that our heating was successful. Continuing with the second heat treatment, we found the almost same behavior. Unfortunately, we couldn't do more indentations, but we found that it's the same behavior. And in the last one, which is the third heat treatment, which is one of the hardest one, must be the hardest one. Luckily, we found the same behavior as the one of 900, and we see that this material, this heat treatment, was way better than the 900 because the material at overall had better properties than these two others.
For analyzing the phases and the temperatures in the carburization test, we're going to use the carbon steel diagram. As we can see here, we have 1018 steel, which means that we have around here percentage of carbon, as we can see here. Okay, with the first heat treatment at 900 degrees, we have this phase, which is gamma plus ferrous carbide. Gamma actually means austenite, and it's a thing that forms when carburization processes happen. To the second heat treatment, the phase is still the same, austenite plus ferrous carbide. Okay, here's the interesting thing. When we do the final heat treatment, which is going to make our material much harder, at 200 degrees, which is around here, the phase changes. It changes to ferrite plus ferrous carbide. This happens because of the third heating of the material, and because the composites we put, like carbon and the other chemicals. As we know, this type of reaction is an eutectite reaction because it only involves solids. Also, this carburization processes is we get to an hypoeutectoid steel. What does that mean? It means that it has less than 80% of carbon in the steel.
There are several terms that we used during our practice that must be defined, such as carburizing, that is when an steel alloy absorbs carbon when it's heated with, in the case of our practice, the mixture that we used, or carbon equivalent, that it's converting all the percentage of alloying elements in the alloy to its carbon equivalent percentage. The carbon potential of an atmosphere is defined as the carbon content of a thin sheet of pure iron in equilibrium with the atmosphere. Also, cemented layer, it's this superficial layer of the steel which properties are enhanced once the carburizing or the heat treatment is complete. The hard cover is also this hard cover of the steel that it's harder once the process is done. To quench, it's cool a piece or an element in a medium, such as water, oil, or any other element that helps to lower the temperature. To temper, it's to cool also a piece, but naturally, just leave it at ambient temperature. And diffusion is the movement of atoms from one place of high concentration region to another, to the lower concentration region. The application of cementation in the metal mechanical industry it's mostly for pieces that are under conditions of variable loads or friction. The cementation steels are the ones that have low content of carbon and have an increased superficial hardness and resistance to impact. There are three types of cementation. Solid cementation, that it's the one we use in our practice, and it's used when you want to achieve a thick layer of cementation. Then there's liquid cementation, it's faster than solid cementation, and it makes the layer more homogeneous. And there's gas cementation, that it's faster than the other two, and it's ideal for mass production of pieces.
They exist basically two types of furnace used in the industry for gas cementing, which are the continuous furnace, which allow the company to have a big production of parts. Basics. No, espérate. They exist basically two types of furnace used in the industry for gas cementing, which are the continuous furnace, which allow the company to have big production of parts, and the second one is the basic furnace, which is the traditional process in the industry because of the opening and closing to extract or take the pieces that are already heated. This allows to also create big productions. The cemented carbides are a range of composite materials which consist of hard carbide particles bonded together by a metallic binder. The proportion of carbide phase is generally between 70 to 27% of the total weight of the composites, and its grain size average between 0.4 to 10 micrometers. The cemented carbides combine the high hardness and strength of a mechanical carbides or carbonitrates with the toughness and the plasticity of a metallic alloy binder, in which the hard particles are eventually distributed to form a metallic composite. Most of the time, carbides cure will leave a bare surface finish on the part and allow faster machining than high-speed steel or other tool steels. Carbides tools can withstand higher temperatures at the current workpiece interface than standard high-speed steel tools, which is a principal reason for the fast machining. Also, carbide is usually superior for the curing of tough materials such as carbon steel or stainless steel.
In this practice, I learned that the carburization process is a complicated one, but also quite extensive. Like the whole process of putting in the oven and increasing the hardness of the material, it's one of the toughest things I think of this practice. And also it's quite interesting the results, like the whole process of making higher the hardness of the steel, of the material. It's something interesting, and I think it's really useful for the industry and life.
In conclusion, this is a very useful treatment because you can adapt a lower carbon steel to wherever you need depending on a concentration on the carbon you want to add it to the surface, because if it's soft you can harden with this heat treatment without changing or affecting the properties of the material, having a soft nucleus and a hard surface.
In this practice, I learned about the cementation process and how important is a heat treatment and how you apply the treatment. You have a different result if you quench or temper your piece in some way, or if you heat to different temperatures and you leave different time of heating in an oven. So either way for your process, you're going to heat in a specific way and apply a treatment to obtain specific results.